Were you able to figure that out, Kurt?
No. Not yet. No.
Okay.
We'll come back to it.
Okay. Yeah. Check out that those example models.
While you're blaming me, you're spilling all over. Don't worry, I'll clean it up. I got it.
But no, that's fine. I go and get it. It's the bathroom is here.
Yeah. Okay.
Thank you.
Okay. So, ladies and gentlemen, I did want to emphasize this slide, which I went over briefly. You'll recall this distinction between endogenous, exogenous, and ignored or excluded factors. And again, these motivations for including factors in a model are quite common sorts of considerations. So again, if it's key to causal, it's posited to be key to causal pathways. If it's needed to capture the effect of an intervention, so you have an intervention that intervenes in a particular place in the causal pathways on a particular factor, then representing that causal pathway or factor is often important. If you're interested in how it gets affected by an intervention, or if you need to capture who is affected by interventions in different ways, being able to distinguish these, particularly for transfer effects from one group to another, capturing those heterogeneities may be pretty important. If a factor is observable in the real world and you want to be able to develop confidence in a model, then incorporating that factor within the model may give you another way of grounding that model, of developing some confidence, or at least of saying, it's missing something important. And if it's very important for stakeholder credibility, important for stakeholders to have some basic confidence in the model, may incorporate one of these factors. So, for example, it may be that for your hypotheses, capturing GIS context isn't nearly as important, but for stakeholder credibility, being able to capture some aspects of the location of individuals and of resources would really enhance the buy-in by the health region or health district you're working with. That's an important consideration to think about. It doesn't mean you automatically should put it in, but it's something that you want to keep in mind. So how about this distinction? So these are factors actually for factoring into model either exogenous or endogenous. Why would we keep something as endogenous very specifically rather than pre-specified? Well, if we want to understand the effects of interventions on this, the ripple through effects of interventions on it, we need it to be endogenous. We need the model to produce it. If we want to be able to understand how the model dynamics will change under a broad set of different assumptions with respect to this factor, maybe the factor has something to do with people's contact patterns, and we're interested in how interventions will affect those contact patterns. Maybe it's advisories about the risk of mosquito-borne illness, or maybe it's factors having to do with warning about flu, high flu rates. And it may not be sufficient for us to view those contact rates as fixed. We might want to see, okay, how does that type of intervention affect things? We might want it to be endogenous there. We could either put in a fixed assumption about how it affects contact rates, or see how it emerges, the changes to contact rates based on behavioral decision making. Something Kurt may be able to brief us on later today. And if we want the model to be able to translate it to other contexts, rather than hard coding the assumptions about that, having them emerge out of other features of the contact may be desirable. The danger here is the more things we make endogenous, the more that takes away from other components. It requires more implementation work, more data potentially, but at the same time does allow for translation to other systems. Okay, I don't think I'm going to go into these. I give some examples here about different levels of scope that you could undertake for certain types of needs. Here, for example, we wanted to model HIV spread. I've been involved in 3 or 4 different models of HIV spread over my time. And if we want to understand the impacts of condom use prevention, promotion, then we need to represent differential transmission risk with and without condoms. Right? I mean, we want to understand how will promoted condom use affect things. Then we need to say something about how it's going to affect transmission risk. Otherwise, we won't have the ability, the lens, the ability to see the results from that. For needle distribution, if we want to examine the effects of safe injection sites or distributing free clean needles to people, we need to be able to capture the impact of needle availability on likelihood of sharing needles. We need to posit something. If needles are available for free, how will that change behavior so that we can ask about the ripple through effects on HIV transmission? So you can see here that the type of intervention we wish to investigate can end up having impacts on what the scope of the model is. If we want to understand how promoting the use of antiretrovirals might affect things, we want to have some understanding about how adherence to antiretrovirals might affect a person's transmission at a causal level. At least have some posited connection there. Okay, so if we were dealing with a situation where we're interested in tobacco policy, tobacco nicotine policy, we could imagine a model on the one hand that has hard-coded uptake rates. Another type of model might have uptake rates dependent on the prevalence of smoking in a group. So the idea here is that rather than being fixed for my age group, sex, and maybe socioeconomic status, we assume this incidence rate of starting smoking, of uptaking, of initiating smoking. That would be the first one. We can instead imagine a situation where the model posits that my uptake likelihood in my age group is dependent on what fraction of other people in my age group smoke. That might allow us to understand ripple through effects of interventions, right? If we can get one person to stop smoking or to avoid initiating, maybe that will mean more than one person gained, because that person who does not start smoking will no longer serve to influence towards smoking another individual. So there may be ripple through effects that we could capture with this. Knock-on effects of preventing one person from stopping smoking, you're preventing 1.2 people from starting smoking because you've eliminated some of the peer effects. Or you could consider a model where uptake rate is dependent on preferences, and some of those preferences depend on peer pressure with positive feedback involved. Others depend on family history of smoking. You can imagine expanding it further, or having it depend on my specific social networks, who specifically is in my social networks. The first of these and the second of them, that can be readily captured in an aggregate model. And indeed, there are models with which I have been associated with both, where exactly that was done. So some of my early work and with the tobacco policy model in the States was exactly these two types of things. It was an aggregate model, an aggregate system dynamics model. But to capture this last one, the social networks, figuring out where to intervene in a social network, maybe having peer educators that we pick based on aspects of social network position, or trying to change the social network in some conscious way, that might require an individual-based lens. Again, we could have aggregate models that posit mixing between populations on hard-coded rates, or have a term which allows for differential risk perception. And again, so for infectious disease models, often we're concerned about mixing between different groups. We could have a mixing matrix that just says, for people in this group, 10% of their contacts are with people in this group A, 20% with group B, 50% with group C, and another 20% with group D. We could have a mixing matrix, and that's a classic way to represent it. Another way, that's one step removed, is a preference matrix. And this basically will allow for the fact that maybe there's changes in how many people are in group A and B and C over time. And you know, if there's only one person in group A, it's hard to believe I'm still going to have 10% of my contacts with that one person. So a preference matrix would allow us to kind of capture preference for spending time with certain people, but if there's fewer of them, I'm going to be spending somewhat less time with them. Or you could have a system which includes mobility. So who I contact happens to be an outcome of my mobility patterns. But maybe my mobility patterns are based partly on who I want to meet with. There's interesting sort of interactions of mobility. The point is, once again, we could have a model that's more confined, or a model that's richer, more inclusive, but involves more mechanism, more extensive components. You know, one has to be careful about where one chooses to build things, and you might start in my own predilection, my own tendency here, and I believe I can speak for my senior colleague as well, is to start very, very simple, and to start, you know, in a model where there's very few endogenous factors, and to learn from that model and work downwards to more detail. Because what detail you put in will be informed by that learning, instead of just, you know, by some guess as to what we'll need. It will actually be informed by what we've learned along the way. I have something here for capturing certain types of zoonoses as well. Okay. And I'm not going to go into that. Time is a fleeting, and the day will soon pass. There's an interesting thread in the literature by Volker Grimm on pattern-oriented modeling, and this is a type of modeling where, you know, he argues that in order to develop confidence about a model, you want to tap into patterns that have been noted about the system being modeled. These are sometimes termed, particularly in the Michigan context, stylized facts. And in system dynamics, we make a lot of reference to reference modes. How does the system behave over time? Is there, not so much in a numeric way, but in a sort of rough way? Are there oscillations? Is there a sort of a growth and then a collapse? Is there initially a high value and then it decays? Is there an increase over time? These are sort of facts having to do with patterns over time. And in pattern-oriented modeling, and Volker Grimm has generalized this to talk about patterns over space or over networks, etc. And he works in the ecology area, and so he points to patterns there that a model might be expected to reproduce. And these patterns, again, per our discussion yesterday on calibration, we're not asking necessarily a model to predict everything about these patterns, but we're actually asking it to capture, in many cases, the phenomenology. The fact that there are waves, that there are clustering exhibited, etc. And there might be certain features of that clustering. So we seek a model that will stay true to those patterns in some sense. Okay. Volker Grimm argues that patterns are pieces of information that can really inform a model, and the idea is that we falsify models by questioning models that don't create these patterns. It's a different take on modeling than I normally undertake, but it's one you should be aware of, and it's fairly articulately specified both in a book and in his article in Science. Volker Grimm. The last name is Grimm, and his first name is Volker, Volker. Okay, So the idea here is we're trying to develop confidence in a model by seeing it reproduce salient patterns, and I put a caution on the word salient here because we have to stop somewhere. But the idea is we use it to kind of capture the features of the situation that are evident from observation, even when we don't have data quantitatively about all of them. Okay. So the idea is we build confidence in a model through that. And these are some examples of patterns that we might see, dynamically that we wish a model to reproduce to develop confidence in it. Okay, I think I'm probably going to stop here. I will note that, ladies and gentlemen, with a nod towards any logic, when it comes to model mapping, in addition to those techniques that we presented earlier, and in addition to Jeff's incredibly copious sort of model maps that he's created on Access to Insight of sorts, sort of mappings of a system, we do have a broader set of languages to draw on. And I really should have reproduced those earlier agent-based hybrid modeling approaches here, but this is something called a system structure diagram. This is common in system dynamics, where we have stocks mixed with causal loop diagrams. But there's also other features. This is from my student Yuan Tian's work. Yuan is one of my foremost students and is leading this project for our Ministry of Health right now on modeling. Remarkably strong contributor, and she as part of her thesis, used a variety of maps. This is one thing she created for a TB contact tracing context, and she's mapping out this process over time: first skin test, second skin test, clinical review. You could argue that this serves as kind of a template or map for some of the more defined discrete event components that might be captured in a TB model. Also, ladies and gentlemen, the types of state charts that we've used in this class can be very useful as qualitative characterizations of a model, or semi-quantitative. And you saw, in fact, that Jeff and I had folded those into that agent-based and hybrid modeling mapping. But these are really useful things. Long before you actually build up the model quantitatively, long before you actually instantiate them with quantitative values, you can draw these out to illustrate features of dynamics. Quite nice for illustrating things. And there's a notion from computer science of a class diagram, which can kind of describe instead which components of the model have which responsibilities. Like a person here as an initial age group, it has an indication whether they're what's called a registered Indian or First Nations person. It's a legal term for First Nations. What their sex is, what their age group is. And this kind of gives the information about what properties, including parameters, are associated with the person. And then we have something for main. This is kind of a way of mapping out your model as it comes into being. These state diagrams, I didn't really go into it in this boot camp, but they can be very, very complex. And there's a model that I think I ended up eliminating because it doesn't work well with any logic 7, but I'm glad to share with people, which has very involved and actually very clear in many ways diagrams for individual deer behavior using state charts. That's the one illustrated there. And you'll notice that it has hierarchical components. It turns out in state charts you can have hierarchies, and they afford an economy of mechanism. In the sense that you can have, like this state chart, rut movement. So I don't know if in Australia, do roos go through rut? Do they exhibit unpredictable behavior? Like, what do they call it? It's it's not a buck, it's what is it called? A big male?
The male roo.
What is that called? There's a special name for it. What is it? It's called a buck?
Buck? I don't know.
Jeff told me the name the other day.
Oh, the boomers.
A boomer.
Oh.
It's a boomer. So do boomers here go through like phases once a year where they get ornery and they will attack things like people?
I think so.
We don't talk about kangaroos
Yeah.
as much as you think we know. We don't know.
Sorry?
They don't know as much as you think we know about
They don't have
kangaroos.
seasons like other, like the females are basically continuously pregnant.
Oh, they are. Okay.
And then it depends on how much grass there is
Got
and
it.
other like.
That's right. You don't have much winter here.
Yeah, it's not so much seasonal as like how much rain there's been and how much food there is and
Okay.
whether they become fertile.
Right, right. Okay, yeah, because in Canada, we have a very pronounced seasonality. And actually in Africa, they also have ruts for certain ungulates. But basically in rut, an animal, like the males go crazy and they run around and they don't pay attention to their health and they're just like focused on finding the female. It's called rut. It's called rut. And it's terrible. It does terrible damage to their bodies, and they end up in a bad way. But there's a thing called rut movement, and that includes two states. Find female, and then where they're in a female group. Anyway, so this is for males. They find females. For females, they just stick in their group and hope no males find them. But in this rut movement, they can, in either of those states, they can go on to this next state. So with these hierarchical states, we have this kind of economy of description where certain common transitions that are common to each of the substates, we can just write one transition for the whole superstate, the whole conglomerate state. And it's very handy. And you'll notice that in any of these states here, they can become thirsty or hungry. Even when they're in rut, the males will, snarf some grass or something like that, or they'll drink some water. So the point is, by creating these superstates, these conglomerate states, we can end up very neatly representing behavior that would otherwise require lots and lots of transitions. Okay, so here, ladies and gentlemen, you can use state charts to good effect to diagram out sort of thoughts about components of a model. Okay, so I recognize and I apologize that was it really didn't do justice to the issue of model conceptualization. This is an area where Jeff and I have grand plans over the next year or two to really strengthen the boot camps and so on. And our August boot camp and incubator, we're hoping to enhance the materials related to this so that we can get a bunch of models off the ground. It's a tricky, it's a very important and tricky process, but it goes on incrementally. Because remember, over time you learn from the model and you figure out, okay, what should I add in next? It's not a matter of what things are going to be endogenous in your model, what things are going to be exogenous. It's not a matter of committing to that all up front. It's a matter of discovering along the way and adding things in as they present as high priority. And you're learning along that way, and that learning goes into figuring out what do I next put in. Jeff, do you want to make any further utterances on this before I close the chapter?
No, just that this boot camp will be a model incubator. That'll be in Saskatoon at the end of August. For those who
That's right, which is just before rut season.
That's right.
But you'll leave before rut.
So females could travel alone to it.
Jokes aside, there's no problems with that. But yeah, you have to watch out for, if you came 2 months later and you went out into what you'd call bush, you'd have to watch out for the moose. Okay, any other comments on model conceptualization?
No, as I say, it's an emerging area. You often got to start wherever you are and try and work out where
and I think
you want to take it.
Yeah, and one of the best suggestions there is work with someone who's been through that process with respect to several models before. At least get some advice from them on how to work through it. There's a bit of apprenticeship that's advisable there. Kurt's been through it many times now. And Kurt, would you be able to do the GIS next?
As you desire.
Much appreciated. That would be fantastic, actually. The timing would work favorably, I believe. Okay, any questions before we close this right now?
I was only just going to make a comment that from my experience as well, the data you've got can affect what kind of model you can create.
Yes, and this is a delicate issue. It's delicate because model, in my view, model data. Data is important for developing confidence in a model. And I made a reference to this earlier that sometimes I will put things into the model that are long causal pathways. I'll explicitly represent them so that, because I want the model to be able to generate synthetic data from the model that I could then compare with real world data about comparable things. But you're right that sometimes it goes beyond that. Sometimes I'll have data about this area of the system, and maybe I will represent it in a fashion that allows me to kind of to use that data as to drive the model in that area. In other words, to use that, for example, to drive the assumptions about an exogenous variable over time. I think
that you just
yeah.
may not have data.
You may not have to.
You may not
That's
be able
true.
to model things you just don't have data. And
Well-
so sometimes, one of
Yeah.
when I did modelling on geothermal energy, people were saying,
Yeah.
you know, we want you to solve this problem.
Yeah.
But when I asked about it,
Yeah.
like they wanted me to put a location thing, but it turned out to be dependent on flow, and the variation in flow from different parties was so enormous that you couldn't reliably solve that problem at all because there was no consensus around this specific variable. And if there was no consensus around that variable, any kind of modelling you did was useless because that particular variable was so critical to solving that problem. And unless there was consensus around it,
So I would.
I think it's a waste of time.
Yeah, I mean, from my view, it is true that without data to inform them, certain uses of models may not be feasible. Like if someone wants you to give detailed recommendations of the trade-offs in cost and health terms between two policies at a very quantitative level, and they have no data to bring to the table at all, often it's a fool's errand to try to build a model to do that. Just that there's not the data needed for that sort of use. By contrast, there are models which have been built fruitfully where there's very little data, in fact, no data. I mean, the Schelling segregation model, which is available here in AnyLogic, has been a very influential model related to the sociology of neighborhood change. And it's given a lot of insights. Even though, this is in example models, even though there's very little there's very little empirical evidence in it, it is something which has lent insight. So I'm going to do Schelling here, the Schelling segregation model. There it is. This is one of the classic models from sociology, and people have learned a lot from it, even though in terms of explaining certain patterns, even though the amount of data that's in it is virtually, it's basically not empirically grounded. So it's not specific to any one type of specific context. It's just it can illustrate, it can help think through how patterns of segregation, shown here between red and black, emerge from very simple preferences. So it's a model that, it's a theoretic model. There's very little data, there's no data essentially that was used to inform it other than rough, very rough guesses as to what parameter values would be. But it's been very influential for certain uses. But it would be a fool's errand to try to use this model to make decisions about policies involving zoning and segregation in LA or Detroit or something. It's just not, it doesn't have the requisite resolution to be used for those purposes. But for the purposes of learning, it can give a lot of insight, I would say.
Yeah, I was going to say, don't think of modeling as just the model. It's the whole process. Like the conceptualization. You may identify areas where you need to then go out and get the data, right? Or, that can lead to that sort of thing.
I suppose it depends on whether or not you are working on it's also about what you tend to tell people. Say, I want you to solve this problem.
Exactly.
And you need to explain to them that problem can't be solved.
Yes. Yeah, so I can't solve that problem, but I might be able to address this. I might be able to work to to help identify, an important uncertainty, or help you think through where the big gaps in the literature are.
And I would say,
with
I
respect
can't
to
solve
this.
that problem right now, right? There's no such thing as you can't solve a problem.
Yeah, I mean, I think in
Fair
the
enough.
case that there were lots of issues around the fact that they were developing a new technology and people were claiming and building based on certain numbers, like 60 and 120 litres per second, when the latest, anywhere in the world, the biggest number they had was 10. And so,
So you can build models with different parameters, try out different things.
yeah, you can, but they just would have linearly scaled, and it wouldn't have, and the question was where to build the best one, and you can't answer that if you can't reliably tell me what that particular number is.
I will readily say there are certain needs for modeling that are not compatible with, if you don't have the data, you can't deliver on this sort of need or that sort of need in certain cases. And that's a hard thing for modelers because they're often enthusiastic to build a model, but sometimes you got to say this is not feasible with the existing state of evidence. But it could be that you could use it for a different purpose, and it could be that it would be useful in a few years' time if only we could gather information about certain things. So I wouldn't say, one thing that modelers do sometimes get caught up in is that all models are used for certain delineated purposes. And I think there's a fair breadth of model uses out there, and some of them are have a strong need for data, and others a lot less. And it's up to us as modelers to warn a client or warn a stakeholder when it's not feasible. And I've been in situations like that where I just say, look, there's just not the evidence that we can bring to bear to reliably build a model that will do what you want it to do right now. But we could learn something about maybe where those gaps are by thinking it through, and maybe in a few years' time, if there were really big primary data collection efforts, we could actually get somewhere in terms of estimating these things. But yeah, we have to speak advisedly to those who want to build models that sometimes what they hope to get out of the model is not feasible, even if they've seen other models used in that way. Okay. Okay. So I'm going to stop here. And Kurt, do you want to come up?
We'll be back in about half a minute.
Okay.
He just went out there to get me and then get some tea, I think, so.
Oh, I see. Okay.
Oh, there we go, perfect.
Okay, great. Yeah, because it will be an all hands on deck thing.